So this is the symbol which we are going to use, or which our textbook is going to use in order to denote the directional derivative. Now, by definition, so the definition which we saw last time, this is the limit as h tends to 0. So u is a unit vector which has coordinates a and b. Now, by definition, this is the limit f of x0 plus ha y0 plus hb minus f of x0 y0 over h. I think last time I said something wrong. I'm not so sure. I cannot check the tape, so maybe when the tapes are online, I can check whether I really said it wrong. But so you have to. What is important here is that u is a unit vector. Otherwise, this formula is not true. Okay, so you have to look at the picture in order to see this. So why do you need that u is a unit vector? So actually, once more, the directional derivative. What is the meaning of the directional derivative? So you have a function of two variables. And this is what you see here. The blue surface is the graph of this function here. Then we fix a point. So you see here the point P on the surface. And you fix a direction. So the direction is given by u. Now what you do is you slice the surface with the plane, this yellow plane here, which you see, which is perpendicular to the xy plane and which has the direction given by u and which is passing through P. And this will, if you slice the surface with this plane here, you will get a curve, space curve C. Now, the meaning of the directional derivative is the slope. So if you look at the tangent to the space curve C at the point P, then the slope of the tangent at the point P is the directional derivative. So this means if you're standing on the surface at point P and you are walking in direction of u, okay, then this gives you the rate of change of the function. Now, why do I need that u is a unit vector? Because actually I'm just interested in the direction. Okay, so it doesn't seem to be that it's not really important that u is a unit vector. The reason is because I want to compute the slope here of the tangent. Now, how can I compute this slope of the tangent? So the usual approach is I fix another point on the curve C, call it Q, and then you project those 2 points down. Okay. Now you see if you denote, so here P prime is the projection of P onto the xy plane, and Q prime is the projection of Q onto the xy plane. If you project this down, you get a vector from P prime to Q prime, and this vector, of course, by definition, must be a multiple of u. Okay. So this, I didn't need that u is a unit vector until now. But I want to approach the slope of the tangent, okay, by looking at, so actually I replace the tangent by the secant. This is the usual approach, the secant which passes through P and Q. Okay, and I compute the slope of the secant instead of computing the slope of the tangent. And then I let Q tend to P. This is what I do. Okay. So if you look at the slope of the secant from P to Q, okay, so the slope of this secant is given by, okay, you have to look at the function value at P minus the function value of Q, and so this is this here, and you have to divide by the length which you get if you project those 2 points down. Now, since u is a unit vector, okay, our h is the length of the vector h times u, which is equal to the projection of the vector p prime q prime. Okay. Otherwise, if u is not a unit vector, it's not necessarily true, and you have to change here the denominator. Okay. That's the reason why we need that u is a unit vector. This is important here. Okay. And I know because in previous Hoykaus we had these very easy examples where you have given a function, you have given a point, you have given a direction, and you should compute the directional derivative. And the direction which was given, the direction was given by a vector, something like, for example, I plus j, okay, where I and j are the unit vectors. So for instance, compute the directional derivative of some function at some point in direction of I plus j. Now you have to notice that the direction, if you have given such an example, you have to notice that the direction is not necessarily a unit vector. And if you want to use the formula which we have seen last time, so the formula was, if f is differentiable, so last time we saw that you can use the gradient times u in order to compute the directional derivative, where the gradient is defined as the vector of the partial derivatives. Okay, so if you use this formula, you have to make sure that u is a unit vector. Okay, and we had such examples in previous Hoek house, and surprisingly, very easy example, almost trivial, but surprisingly, not many students got the right answer, and I'm pretty sure what the mistake was. Namely, most of the students forgot to, from the given vector, to compute a vector which has unit length and the same direction, to change to a unit vector. So this is important here, okay? So you, the u must be a unit vector. Okay, otherwise, this will become different here. So I said this, I think I said this last time. I said this wrong. I said at this stage it's not important that u is a unit vector. In fact, it is important. Okay, because otherwise the meaning of this fraction here will change. Okay, so any questions to this? So you see, but this is the definition of the directional derivative in direction of the vector u. And last time we saw already that if f is differentiable, then all directional, if you have a differentiable function at the point P, no matter in which direction you are walking, okay, the directional derivative will always exist and can be computed by this easy formula here. So it's the inner product of the gradient with the vector u. So this is the direction you consider, where the gradient is defined as the vector which has its components, the partial derivatives. Now, last time I already, at the end of the lecture, I already told you that here an interesting question, natural question, is whether the existence of the directional derivative in any direction implies that the function is differentiable. So if the directional derivative at some point exists for all u unit vector, does this imply that f is differentiable? Okay, so this means that you are standing at a point P, and no matter in which direction you look, you always have a derivative. Does this already imply that the function is differentiable at this point, at the point you are standing? And I told you last time that this is not true. Let's look at an example. For instance, an example is this one. Okay, so let's first check whether it's really true that for this function at the point 0, 0, all the directional derivatives exist. You have to notice, okay, for this you are not allowed to use the formula, okay, because f is not differentiable at the point 0, 0, because f is not even continuous at the point 0, 0. So first, note that f is not differentiable at 0, 0. Okay, we discussed this example before, because if you approach 0, 0 along the parabola x is equal to y square, you see that here, if you plug in x is equal to y square, you always have 1/2, whereas the limit should be 0. Okay, so the function is not continuous at 0, 0, so the function is also not differentiable at 0, 0. So if you want to compute here directional derivatives, okay, you're not allowed to compute first the gradient. The partial derivatives here exist, okay, because if you plug in x is equal to 0, okay, so you consider as a function of y, then you see everything is 0. So the partial derivative with respect to y is 0. The partial derivative with respect to x is also 0. Okay, so the partial derivatives both exist. The gradient exists, also in the point 0, 0. But you are not allowed to use the formula that you compute the partial derivative as the inner product of the gradient and u, because for this f has to be differentiable, but f is not differentiable. Okay, so we have to, if we want to compute here the directional derivative, we have to use the definition. Okay, so this is the limit as h tends to 0. Now, by definition, f of, so assume that the coordinates of h are given by AB. Then you have here HA, HB minus F0, 0 over H. Okay, so if you plug this in, then you get the limit h tends to 0. So this is 0 here by definition. And for this we get h. So we have here h and here h square. So we have h to the cube, then ab square over. And here we have h square, a square, plus, and here we have h to the 4th, b to the 4th, and everything divided by h. Okay, so what you get is the limit h tends to 0, and then you have h square ab square over h square a square plus h to the 4th b to the 4th. Now here you can cancel h square, and then you get here square. So you see, because h tends to 0, okay, so indeed this exists here. So this is b square over a. Of course, unless a is equal to 0. Unless a is equal to 0. So there is one direction left. A is equal to 0, b is equal to 1. Okay, so this is the direction of the y-axis. But for this is the partial derivative with respect to y also exists. Okay, so you see that here you have that the partial directional derivative in every direction exists, but still the function is not differentiable. Okay, so the existence of the directional derivative in every direction does not imply that the function is differentiable. Okay, actually, this is not very surprising, because you see that the directional derivative is always, you always walk along. If you project your curve down onto the xy plane, you walk along a line. Okay, but you could walk also different. You could leave p. Okay, if you leave p, it's not necessary that you walk on a curve which projected on the xy plane is a line. You could walk different. Okay, and differentiability should mean that no matter how you walk, okay, unless you should walk on a continuous curve, okay, a smooth curve, the derivative should always exist. Okay, so intuitively, this should be wrong here, and this is a counterexample. we had in the previous Hoikau we had this question. So I think 4 statements, and you have to figure out which one is wrong. And one statement was this here. Actually, it's not hard here to find the counterexample, but it's also not completely easy because you have to choose something like this here. If you choose xy over x squared plus y squared will not work, because if you choose xy over x squared plus y squared, then you will see that certain directional derivatives do not exist. Okay, so you have to choose something like this here. This is maybe the most easiest example which shows this, at least the most easiest example I could find. Maybe it's possible to find a more easier one. Okay, so any questions to this? Now in higher dimension you can do the same, but of course you do not have such a nice picture anymore. So for instance, for a function of 3 variables, okay, so again you can you can define directional derivatives of f at some point where u is now a vector in the space, and also must be a unit vector. And this will be defined similar. You take the limit, h tends to 0, and then you have f of x0 plus ha y0 plus hb z0 plus hc minus f of x0 y0 z0 over h. And again, if f is differentiable, then this can be computed as the gradient. The inner product of the gradient with u, where the gradient here is now defined as is also a vector in the space with coordinates, the partial derivatives. Okay, so and similar for higher dimensions. Okay, so if you have dimension 4, 5, and so on, a similar definition, but then you it's maybe better to write this here in vector notation and not in not writing out all the coordinates. But similar, you have something similar in higher dimension. But since in higher dimension we do not have any picture anymore, so here you can interpret this as a rate of change. Okay, it's no problem. Also in higher dimension you can interpret this as a rate of change, but not as a slope anymore. But since in higher dimension we do not have any picture anymore, here at least we can, of such a function, at least we can plot the level surfaces. But if you have a function in 4 variables, you do not have any picture, any way to depict it. So we will stick to the situation dimension 2 and dimension 3. Now, here, so far we have introduced the gradient just as a convenient notation in order to write this here, because if f is differentiable, we prove that this is equal to, this is just using the chain rule, fx times a plus fy times b plus fz times c, and we just introduced this here as a convenient notation to write this expression very neatly and shortly like this here. But as you might already know from applications, the gradient is a quite important object, and it has several properties which makes this object here interesting. The first question is, or the first property arises from a very natural question, namely if you are standing on the curve at a point P, okay, now you want to know in which direction do you have to walk such that the rate of change is getting maximal, okay, then it turns out that this direction is given by the gradient, and the rate of change, the maximal rate of change, is the length of the gradient. Okay, so this is this result here. So direction, directional derivative is maximal for u in direction of the gradient of f, and the maximum value is given by the length of the gradient vector. Now, this is something which is almost trivial, because you see that by the definition of the inner product, so this is equal to the length of f times the length of u, but it's a unit vector, so 1 times the cosine of the angle between u and the gradient. And you see that this is getting maximal if this is getting equal to 1, which means that theta is equal to 0 or pi, and this means that u must be in direction of the gradient, and this is the pi is not true because pi is -1, but so it's 0, and the maximal value is given here by the length. So this, of course this is trivial. You immediately see this from this definition here. I have already stressed last semester that you have a disk which comes with the textbook. So I haven't used the disk very often in the lecture. This does not mean that it's useless. So there are some tools on the disk which are quite nice and which can help you, because this is called tools for enriching calculus, which can help you to enrich your understanding of calculus. Now you see we need multivariable tools. Now this is our textbook here. You see, you have quite a lot of tools here on the disk. I'm not sure whether you even looked at it. For some tools, I think you can get some hints for homework assignments and so on. Now here you have quite a lot of tools which are related to every chapter, which help you to get a better feeling for functions of two variables and their properties. For instance, you have something where you can draw level curves and so on. What I'm interested in is this here, maximizing the directional derivative. I'm not sure whether it will work. Okay. Now you see this will give you here. So what you have here. So first I have to explain you what is a good angle to look at this. Okay. Also, this is not a perfect angle, so maybe this one. Now, what you see here is you see the graph of a function. Okay, so this the shaded area here is the surface of a function of two variables. Now, what you have is you have fixed the point. This is the point which is here purple. Okay, so on the surface and in a certain direction, which is given by the blue vector. So the direction which we consider here, this is three-dimensional. But if it's two-dimensional, I mean, if we have two independent variables, then the plot is in the space of the graph. But the direction u which we are giving is a vector in the plane. So you have to look at this vector in the xy plane. So you see that the blue vector gives you the direction in which you are looking. And for this direction, you also see here the blue in blue the tangent at this point in this direction. Okay, And the yellow vector, what is the yellow vector? The yellow vector is the gradient. Okay, also, of course, in the plane. And you have here this kind of marker which tells you, so this red one, which tells you at this point, which you are looking at the moment, so for this tangent, what is the slope? And you will see here how it changes. Now, I can start this. Okay, so now the direction in which you're looking is moving. Okay, so you see also the red marker is going up and down, and you see what we want to understand here is okay, where is the directional derivative, or where is the directional derivative as large as possible, and this should be when the blue vector coincides with the yellow one, because the yellow one is the gradient. Okay, so you can now that it's going down. Down, down, now it's going up again. Okay. Now you have the maximum, and then it's going down again. Okay, so here is, at least here it's true for this, but of course it's true in general because the proof here is very easy. So you see that if you are standing at this point here, at the purple point, and you wanna walk upwards, okay, in the choosing the way which will which will change your height as fast as possible. Okay, then you have to walk in direction of the gradient. So you see, you have on this disk, you have such kind of tools. You can also choose here all kinds of. You have here some explanation. I didn't read it, so I don't know what is going on here. You can choose here different colors. You can choose different functions, and so on and so forth. So you can do here all kinds of things. I guess you can also change the function, and I don't know what else you can change, but this is a quite nice tool in order to visualize some of the results we learn in the lecture. So if you are the visual type, if you need some visualization, this is quite a good tool, and sometimes it's good, even if the result is so easy as this one, okay, the proof is very trivial, it's still good to see it visualized in order to fully grasp what is the meaning of this. Okay, so there are quite a lot of useful tools on this disk here. Now, there is another example in our textbook which also helps you to understand this kind of result. It's worthwhile to look at this example. So what you have given is the function f of xy is equal to x e to the y. And we look at the point 2, 0. Now, we are interested in the directional derivative where u is in direction to some point q, which is 1/2 and 2. Okay, so u in this case, of course, this is a very easy example. So u in this case is, you look at this vector, so 1/2 minus 3/2 and 2. But you have to multiply, because this is not a unit vector, okay? So you have to multiply with the length so you have 1 over square root of 9 over 4 plus 4. So you shouldn't forget this, okay? That you have to multiply with the length, okay? If you want to use our usual formula that this can be computed as the gradient times u. Of course, this here can be simplified. So this is 5/2, 2 over 5. now if you compute, the next thing is always to compute the gradient. So the gradient is the partial derivative with respect to x, which is e to the y. And then you have the partial derivative with respect to y, which is x e to the y. So the gradient at a point 2, 0 is equal to 1 and 2. So the directional derivative is given by this multiplied with the direction here. So what you have is minus 3, 5 plus, and then you have 8, 5, which is 1. Okay, and if you want to know, okay, in which direction is the directional derivative maximal, so this is the direction, okay, and the maximal value of the directional derivative is given by the length of this vector here, which is the square root of 5, by this theorem here. Now, of course, this is trivial. This computation is trivial, but maybe I stress once more. Okay, we had one example in one of the previous Hoik-house, which was as simple as this one. Okay, but only I think 15% or 20% of the students could solve it. And I guess the mistake most of the students made is they forgot to normalize the vector here. Now, so this is kind of trivial, this kind of computation, but something which is interesting is plotting the level curves of this function here. Okay, so I'm not plotting the graph, I'm plotting the level curves. Now, if you do this, what you get is it's a picture like this here. Where here the function values are getting larger and larger. Okay, so these are the level curves. So for these on this curve, the function has a constant function value, and as you move in this direction, the function values are getting larger and larger. Now, if you plot the gradient, you will see that what the gradient is 1, 2. So you will see something like this here, and you will have a right angle here. This is not a coincidence. So if you plot level curves and you plot the gradient at this point, then the gradient will be tangential to this curve here, to the level curve at this point. Now, this is something which is actually easily, using calculus, easily explained, okay, so easily proved. Let's look at the three-dimensional picture. Okay, so in terms of the three-dimensional picture, this should mean that if you do not plot the level curves but the level surfaces of a function of 3 variables, so we have now a function of 3 variables. If you plot the level surfaces, then at a point, okay, the gradient at this point, okay, should be tangential to the level surface, okay. But actually, we haven't defined yet what is this supposed to mean, tangential to a level surface. So of course you know what this means. This means if you're at some specific point, okay, if you look at the tangent plane to the level surface, then the gradient vector is a vector which is perpendicular to this tangent plane. But for this, because actually we haven't defined what is the levels, what is the tangent plane to a level surface. We have defined what is the tangent plane to a function of 2 variables, but not to a level surface. But you can easily extend our definition to the situation where you have given a level surface, where k is a constant. Okay, so you have given this level surface. Now you choose a point on the level surface. So let's say on S. And you choose a curve, so a space curve. Passing through T on S. And C must be smooth, given by the vector function and we assume that this vector function must be differentiable. You should realize we have now several different notations of differentiable. Okay, one for a function of one variable, for a function of two variables, also for a vector function. Which for vector function differentiability just means component-wise. Okay, and we assume that let's say at t0 we will get our point P. Okay, so you have a level surface. This is our surface S, and you have a point on the level surface, and you choose any smooth space curve, smooth enough, which is contained here on the level surface. Okay. Now, of course, what you can do is you can look at the tangent to this space curve. Okay, so the space curve first of all must be on the level surface. So what you have is that f of xt, yt, zt is equal to k. Now, if we are interested in the tangent vector of this space curve at the point P, okay, so what we can do is we take the derivative here, and for this we use the chain rule. So we have the partial derivative of f with respect to the first coordinate times the derivative plus the partial derivative of f with respect to the second coordinate times the derivative plus the partial derivative of f with the last coordinate times the derivative of z of t with respect to t must be equal to 0 using implicit differentiation. Now, you can shortly write this as you see that the gradient of f inner product with, and this is exactly the derivative of our vector function as we have defined it previously, equal to 0. Okay, so in particular, what you get is that at the point t0 you are here. Okay, that the gradient. Yeah, I shouldn't write this like this. The gradient at t0 is x0, y0, z0 of f times. Okay, but this means that at this point, okay, the gradient is perpendicular to all the tangents, okay, which you obtain as the tangents to space curves which are on the surface passing through the point P. Okay, and if the gradient of f is not equal to 0, okay, so this motivates to define the tangent plane to P as the plane which, if the gradient of f is not equal to 0 at this point, which has the gradient of f as normal vector and is passing through this point here. That's the tangent plane for a level surface. And by this observation, the tangent plane to the level surface will contain all the tangent lines which you get to space curves which are smooth enough and go through the point P. This is the plane through P with normal vector gradient of f. Now, maybe once more you might wonder why do we define. So this is a definition here of the tangent plane, but we have to define the tangent plane already previously. But previously we looked at the special situation, namely at the function of two variables. Now this is the definition of a tangent plane to a level surface. Okay. So you see that that the equation of this plane is easily given by this here. So what you have is the partial derivative of f with respect to x times x minus x0 plus the partial derivative of f, because actually not by this here, so because of this definition here. So you have the point with coordinates x0, y0, z0, and you have this normal vector, and then we get that the tangent plane is given here by this equation here. And we also define a normal line. Okay, so the normal line, just that you have heard this expression, is the line through P with direction in direction of the gradient. So this is normally the normal. This is called the normal line, and it's easy to write down equations for the normal line. Now, how does this fit with our previous definition of the tangent plane? You see, previously we looked at such a function, but you can interpret this if you choose f of x y z as z minus f of x y. Then what you're looking at actually is you look at this function and you have the level curve with function value 0. So by this new definition of the tangent plane, okay, the tangent plane at some point, okay, x0, y0, z0, to this lying on this level curve is given by this plane here. Okay, but you see that the gradient of f here for this situation is, maybe I should write it here. Okay. So you see, if you plug this in, then you just get our usual definition, our previous definition of the tangent plane. So this gives the previous definition. Okay, so if you have a level surface, the tangent plane to a level surface is by definition the plane which is given by, which is passing through the point where you are interested to, where you want to consider the level at the tangent plane, and a normal vector is given by the gradient. Okay, and this plane, this definition makes sense because this plane will contain all the tangents, okay, which are given by smooth enough space curves which pass, which are tangents to smooth enough space curves which pass through the point P. So this is a definition which we will need later on for the tangent plane of a level surface. But so this is one way to look at this. But the other way is we just have proved that the gradient is perpendicular at some point of a function of three variables is perpendicular to the level surfaces of this function. Okay, so this means that the gradient has two important properties. The first property is that the gradient points in direction of largest increase. Okay, where it points in the direction where the function is changing. Is changing where the change of the function is maximal, okay, and the tangent, the gradient is perpendicular to the level surfaces. Those two properties, and of course, from one property you would guess that the other is true and the other way around, because if you look at this, So this is in the space. Maybe in the space things are harder to visualize. So let's return to the plane. And let's summarize. Properties of gradient of f for a function of two variables. First, direction of fastest increase. And second, perpendicular to the level curves. This is the picture which we saw for the function e to the x times e to the y. But this is something which is not very surprising. Okay, if you look, for instance, if the meaning of your function is okay, the elevation, so you have some landscape, okay, and this the set means the height on which you are standing. Okay, so for instance. And so on. So these are the level curves, okay, of some function. Now, if you interpret them as okay, so here the height is maybe 100, here the height is 200, here the height is 300, 400, and here 500, and so on. Okay. So this is some landscape, and here you have some hill. Okay. Now, if you are standing here at this point here, we know if you want to go. If you want to reach the summit, okay, as directly as possible, okay, then you have to turn into to the direction, okay, which is given by the gradient vector, okay, because this is the direction of fastest increase, and this is something we know already. This is a principle which we know from hiking, okay. So normally the direction we have to go is perpendicular to the level curve we are standing. Okay, so here the gradient will be like this here, and then here we will walk like this, and here we will walk like this, and here we will walk like this, and here we will walk like this. Okay, so this is the gradient. The gradient tells us the direction, and the gradient is perpendicular to the level curve. It's not a surprise. Okay, so this is something which we know when we go hiking. Okay, if we want to go to the summit as direct as possible, okay, we will walk in the direction which is perpendicular to the curve of the same level we are standing at the moment. Okay, or in mathematical terms, we have to walk in direction of the gradient. Okay, so actually what you could do is because you see that the gradient is a special function which attaches to every point in the plane a vector. Okay, so you have for every point in the plane you have a vector here attached to this point here. It's a kind of generalization of a vector function. Vector function is for is from the real numbers into the set of vectors, and here you have from the plane into a set of vectors. So you see that for every point here, you have a vector attached, which is given by the gradient. Okay. Now, something like this is called a vector field, and for instance, programs like Maple are able to plot for given function the vector field. Okay. Now, if you would plot the vector field here, normally Maple is plotting this in a way that, of course, Maple cannot for every point attach a vector. Okay. Otherwise, you would see nothing. So just for certain points, Maple chooses certain points and attaches the vector, okay, and indicates a small vector the direction here. So if you would plot, and I think you have a plot in the textbook of this vector field here for this situation, then all the vectors are pointing uphill, and because of this property, all the vectors are perpendicular to the level curves. So these are the two important properties of the gradient vector. We will see some more applications of the gradient vector later on when we talk about the method of Lagrange multipliers. Okay, so any questions to this? Now, this is essentially everything I wanted to tell you about directional derivatives and the gradient vector. You see, when we talked about directional derivatives, we just used the gradient vector as a convenient notation in order to shortly write our formula which we got for computing the directional derivative. But it turned out that the gradient is an object which is interesting in its own right, because it has some interesting properties. Just to summarize, okay, you should see directional derivatives as a natural generalization of the partial derivatives. Okay, because partial derivatives are just in two directions. The partial derivative with respect to x is in direction of the x in the x direction, and the partial derivative with respect to y describes the rate of change of the function in y direction. And the directional derivative, okay, is a natural generalization where you look in other directions. Okay, you look in an arbitrary direction. Now, the important information is, of course, there is some relationship between existence of directional derivatives and differentiability of a function. Namely, if f is differentiable, all the directional derivatives exist. Okay, you can easily compute them by a very easy formula. But we have seen the inverse is not necessarily true. So if even so, the directional derivative in every direction exists, the function is not necessarily differentiable at this point. Okay, the reason being that you just look at certain direction. I mean, of course, you look at all directions, but you leave your point just on specific curves, okay, which projected on the xy plane are lines. That's still not enough to ensure that the function is differentiable. Okay, so what we want to do next is we want to apply what we have learned so far, and essentially we want to discuss similar questions to the questions we have discussed already last semester. Namely, we want to figure out how to use the tools we have developed so far in order to find maxima and minima of functions of two variables and functions of more than two variables. So actually, we more or less we concentrate on functions of two variables, because for functions of three variables we do not have a way to depict the graph. Now, for a function of two variables and some point in the plane. Okay, so we have similar definitions for local maximum, local minimum, local maximum value, local minimum value, absolute maximum value, absolute minimum value. So the local maximum, so AB is called local maximum. If f of xy is smaller or equal than f of AB for all xy close to AB. Okay, and similar we have so this is local maximum, and f of AB is then called local maximum value. Local maximum value. Similar. Local minimum. Local minimum value. you have to note this kind of definition is similar as last semester, okay? Because now the domain of our function, okay, f is a region in the plane, okay? So normally the domain of f is something like this here. Now, in order to consider local maximum and local minimum, okay, what we assume is that the point AB is not on the boundary. Not the boundary here is the boundary should be clear, is like what you have here, okay. So normally what we assume is that AB is inside D, okay. So this means inside. Actually, there are precise mathematical definitions for a point is called a point which is inside, a point which is outside, a point which is on the boundary, and so on. But for us, inside, a point lies inside of D. It just means that you can find a small enough ball around the point such that all points inside the ball also lie, not ball, sorry, disk, such that all points inside the disk lie also inside of D. Okay, this means a point is in mathematics we call this interior point. Okay, so such this definition just for points which are really inside of D. Okay, which means because of this here, so for this has to hold for all x, y close to AB. Okay, this kind of not very precise notation means that you can find a disk around AB such that this holds for all x, y in the disk. Whereas global, you have a similar definition for absolute maximum, absolute minimum, and absolute maximum value, absolute minimum value. Of course, the notation of absolute maxima will greatly depend on what is the domain of the function f. And for absolute maxima, we also allow points on the boundary. Okay, so this is completely similar to what we have done last semester. Okay, and we also call local maximum and local minimum we call local extrema, and absolute maximum and absolute minimum we call absolute extrema. And these values we call local extreme values and absolute extreme values. Now, the first observation is that we have here something similar to what we called last semester the Fermat's theorem, which will be already helpful in order to locate local extreme values. So first we will look at local extreme values. So first we are concerned with the problem of finding local extrema. Now, last semester we had this. We had Fermat's theorem, which told us if the function is differentiable at the point and has a local extrema in the point, then the derivative must be equal to 0. And you have here something similar. So if f is differentiable, sorry, I should say, if the partial derivatives of f exist at the local extrema AB, then both of them must be equal to 0. This actually, of course, this is just a consequence of Fermat's theorem from last semester. Because if we look at partial derivatives, we just look. For instance, this means we keep the y fixed. Y is equal to b, and we look at f as a function of x. Now, if we know that we have a local extrema, if we have the function f is of two variables, but if we fix b and we have a local if the function has a local extrema at ab, then the following function. So you define a function g of x like f of xb, and you see because of this the partial derivative exists. So this function is differentiable in the sense of last semester, and because f has a local extrema at AB, this function has a extrema at A. Okay, so you just apply the result from last semester. So it's differentiable and has an extrema at A. So from last semester we know that the derivative, but the derivative here is just a partial derivative, must be equal to 0, and similar for the partial derivative with respect to y. Okay, so last semester, what was the next step? Based on this theorem, we defined critical points. And critical points are the sets which possible are local extrema. Okay, so we see here that okay, so because of this result, we just have to look at the points, okay, where both partial derivatives are equal to 0, and at the points where partial derivatives do not exist. Okay, so only those points, okay, are possible candidates for being a local extrema. But again, the inverse here is not necessarily true. Okay, so critical points are not necessarily local extrema, but this will narrow down the possible set of where the function can have a local maximum or local minimum. So this is completely the same as last semester. It's called critical point if or does not exist or if they both exist, then they must be equal to 0. And we see from this result, okay, that if we have a local extrema at AB, then AB must be a critical point. Okay, so if f has a local extrema at AB, then AB is a critical point. But the inverse might be wrong. There is no difference here to what we have done last semester. The last statement might be wrong. Okay, an easy example is the following one. Z is equal to y squared minus x squared. Because you see that, okay, so where are the critical points? So if you look at the partial derivative of z with respect to x, minus 2x, you equate it to 0. And you look at the partial derivative of z with respect to y, it's 2y, and you equate it to 0. You see there is only one critical point, 0, 0. 0, 0 is the only critical point. Okay, so if this function has local extreme values, they must be at 0, 0. But 0, 0 is not a local extreme value of this function, because if you plug in, if you look at the direction where x is equal to 0, okay, and y can change, then you see what you have is a maximum there. And if you look at y is equal to 0 and let x change, then you have a minimum there. Okay, so there cannot be local extrema at 0, 0. But 0, 0 is not a local extrema. Of course, we know this because we know this kind of guy. You might remember the name. This is a hyperbolic paraboloid, and we have seen the graph of a hyperbolic paraboloid. Now, the first step is the same as last semester. First, we narrow down the possible set where extrema might occur. Okay, so we look at the set of critical points. This normally narrows down the choices of the points where we have local extrema. And then we need something like, so last semester we saw there is a first derivative test, second derivative test, and so on. So in fact, we have here something similar. But of course, the situation here is a little bit more is a little bit more complicated because for a function of one variable, okay, you have only one second derivative, but here you have 4 of them. Okay, all the partial derivatives. So how? So you get 4 numbers. Okay, at some point, how do you use the information to decide whether at this point you have a local maximum value, maximum or local minimum or nothing? Okay, so the situation here is a little bit more complicated, but you have a similar result, result to what we call the second derivative test last semester, namely the following one. Okay, so this is the second derivative test. I'm not sure whether the book calls it second derivative test, but it's like the second derivative test. You look at the second partial derivatives. So what you assume is, assume that the second partial derivatives exist at the disk centered at AB and are continuous. Okay, so you need that of your given function, the second partial derivative all exists at the disk which has a center AB and are continuous in the disk. Okay. Moreover, assume that the first partial derivative at AB is equal to the first partial derivative with respect to y at AB is equal to 0. Okay, so we have a critical point at AB. Then, so define what is called D. Now, this is you just look at the partial derivative, the second partial derivative with respect to x times the second partial derivative with respect to y minus the mixed partial derivative square. This is what you saw today in the in-class homework. So this is called D, the discriminant. Then you have the following cases. So essentially you have to look at this at the sign here of this D here. So the first case is D is larger than 0 and the second partial derivative with respect to x is smaller than 0. So if you have this case, then you have a absolute local maximum at AB. Then the second case is D is still larger than 0, but this is smaller than 0. Then you have a local minimum. Sorry, it's this is a minimum. This is a maximum. And if d is smaller than 0, okay, nothing. You have nothing at AB. I should say that I haven't mentioned this, but what is clear is because if the partial derivative exists and are equal to 0, so these are some of the critical points. In this situation, you have to observe that the tangent plane at the point AB is equal to 0. This is something you would expect. Okay, so this is similar to the one-dimensional situation where the tangent is horizontal at the local extrema. Here you have that the tangent plane is equal to 0. And in this case, the function is crossing the tangent plane at AB, and you have what is called a saddle point. So no local extreme. This is called saddle point. So here, in this case, AB is a saddle point. And you see that here there are several cases are missing. D is equal to 0 is missing. And if d is larger than 0, fxx is equal to 0 is also missing. And in those cases, notice you can have both a local extrema or a local maximum or a local minimum or nothing. Okay, everything is possible. So in case d equal to 0, okay, you do not have a decision. This is similar to the case where for a function of one variable, the second derivative equal to 0, then you don't have a decision either. You say where did I? There is the mistake. This is this is larger. This here, yeah, you're right. This is the situation is the same. Yeah, you're right. So this is a maximum and this is a minimum. No, okay. Now I know what you mean. Okay, so this is a maximum, and this is a minimum. Okay, thank you. And just to show you that if t is equal to 0, there is no way that you have such a result. Look at the following function. It's not so easy to. It's not so complicated to find a function which tells you that you really don't have a decision. If t is equal to 0, or who can come up with a function? Who can come up with a function which the critical point, the d is equal to 0, and who can come up with three functions? Who at the critical point d is equal to 0, and for the first function you have a local maximum, for the second function you have a local minimum, for the third function you have nothing. Maybe, of course, a little bit thinking, okay, easily reveals. You look at this function. Okay, it's kind of the same idea as for a function of one variable. Okay, you choose the exponent here large enough. So here, for this one, so this is the first one, then you choose this one. And the third one is you choose this one. Now, for all three functions, you have the critical point 0, 0. Okay? But, 0, 0 is a critical point actually it's the only critical point, okay? Because if you take the derivative here, you have the first partial derivative, you have 4x to the cube. You equate it to 0, you get x is equal to 0, and the same for y. So you have 0, 0 is the only critical point in all three cases. But what you easily see as well is that all partial derivatives are 0. All second partial derivatives are 0. And all second partial derivatives equal to 0. So the d is equal to 0. Okay, but here you have a local maximum, actually absolute maximum, but also local maximum, local minimum, nothing. Okay, so for d is equal to 0, there cannot be a clear decision. Okay, so next time I will show you how to prove this. The proof is not very complicated. It's similar to the proof of the theorem which just mimics the proof of Fermat's theorem. So here we also just rely on results from last semester in order to prove this. And then I will show you some examples. Of course, the situation of a function of two variables is like more tricky. And I will also show you next time using Maple that even if you have access to a plotting device like Maple, finding finding local extrema for functions of two variables is much more complicated than for functions of one variable, because it's largely depends on your viewing rectangle, whether you are able to see from the plot whether there are really local extremas or not. I will show you this last time that even using Maple, it's not so easy sometimes to figure out the behavior of a function of two variables. But using calculus and using these results which I presented today, it's much more. This gives you a much better tool to figure out are there local extrema and where are they. Okay, so any questions? If not, then we will meet on Monday.